So in this video, we're going to recap moments and the equations required for this topic. So the first equation is that moments are equal to the force multiplied by the perpendicular distance. So m is moment, F is force, d is the perpendicular distance. So the units for each of these, force is typically measured in newtons, distance is typically measured in meters. So the units of the moment is basically the units of force and distance multiplied together, which provides you with Newton meters. Obviously you can use prefixes on any or all of these as well. So the classic example for calculating a moment in this kind of introductory type setting is imagining that you have a bolt that needs tightening and you're going to do it using a spanner or something. Alright, so this is my spanner, and what we would expect is that the moment, or the amount that we're able to kind of twist this bolt, or the ease with which, maybe I should say, that we're able to twist this bolt, is going to depend on how far away you grip the spanner. So say you apply a force quite close to the bolt, you're going to have a different moment created compared to when you apply the same force at the end. And that's because you have a difference in the distance over which the force is applied. So say this is like the center of our bolt. The distance here is going to be, I'll call it D1, and the distance here would be D2. And both of these represent perpendicular distances. Reason being is that this force is applied vertically, and we're then measuring the distance back to our point of interest, so the center point of our bolt, let's call it O. So if I dotted it in when it's a little less obvious, sometimes it's good to dot it in, you have this line of action for your force, and what you look for is if you drop a perpendicular line back to your point of interest, the distance of that line is the one you're interested in for calculating the moment. Similarly back here, again, if we have a line of action that we draw in, we're looking for the distance perpendicularly back to point O. So this in here needs to be a right angle, and the total distance this time, which is D2, would be what we'd use to calculate the moment. So hopefully you can see that if for some reason I decided that I should apply a force this way on the handle, my line of action for that force is going to be directly through point O. Okay, this red line here. So if my line of action acts directly through point O, the perpendicular distance, which I would need to apply this equation, would be 0, which in effect means that I'm going to create no moment. And this kind of makes sense if you just look at this situation, because if you apply a force straight down the handle, you're not going to rotate the bolt, you're only going to push on it. So if you're not rotating it, you're not creating a moment. Alright, so that's kind of the basics of kind of how you can conceptualize moments. And now we're going to talk about how you can create or calculate the resultant moment of a system. So let's pretend that you have a system with multiple different forces. Okay. What we can do is calculate the resultant about any point, let's call it O, using the equation that the sum of the moments about that point O is equal to the resultant about point O. Okay, so this is sum of moments. Oh, that should say about O, and this one here is your resultant moment. Okay, so it's very much the same as when we were doing resultant forces last week. You're just simplifying a whole series of moments or a whole system of forces and moments down into one resultant. Okay, so let's say, just give us an example where we had one force for now. All right, and the force is going to be applied like this, F. So if I wanted to calculate the moment about point O, I could do so. Okay, all I'd need to do is take this force F and multiply it by the distance back to point O. So if I dotted in my line of action, something like this, I need this perpendicular distance that sits in here. Okay, let's call this distance D. Yep. Okay, that's this distance in here. So my moment about point O is going to be equal to this force multiplied by the perpendicular distance, and the only other thing I need to consider now is the direction of this moment. So moments can either be clockwise or anti-clockwise, and the normal sign convention is to consider anti-clockwise as the positive direction. This is due to the fact that if you use the right-hand rule, which is where you put your thumb out of the page to represent the positive z-axis, the direction that your fingers point tell you the positive direction for the moment around that axis. And that works out to be anti-clockwise for all problems which are just 2D. So that's where the anti-clockwise is positive thing comes from, but technically for these questions it's not going to matter which way you actually consider, since we're only doing it in 2D. Alright, so if we think about this force F, it's going to be pushing in a anti-clockwise direction about point O. Remember that you need to always consider it with respect to your point of interest. So if this is going to try and push us in a anti-clockwise direction, that's positive, so it needs to be positive in the equation. So the resultant moment about point O is equal to positive FD. Now, there's another way that you can consider this, and which way you use is going to depend on what information you're given in the question. So let's say that we have exactly the same setup with exactly the same force this time, but instead of being given this distance here, what you're given is the horizontal and the vertical distance from O back to where the force is applied. Okay, so let's give them names. Let's call this one D1 and this one D2. It's going to be in your interest this time to split up your force into the horizontal and vertical components. This is because you're then going to be able to utilize D1 and D2, and you don't have to do a whole heap of trig to figure out this other perpendicular distance in here. Okay, so let's do it. Let's split this up. So this is going to be Fy, and this is going to be Fx. So if we sum our moments about point O, let's consider the vertical part first. So we need to consider it as being equal to the force times the distance. So the force is Fy, and the distance from our line of action through Fy back to point O, our point of interest, is going to be this D1 in here. So it's going to be Fy times D1, and then we need to consider the positive or the negative direction of it. So this one here is going to cause a positive moment about point O. It's going anti-clockwise around this point, so it's going to go in as positive. So now we need to consider Fx. So the force is Fx, and the distance that this one needs to be multiplied by is going to be D2. Again, if you dot in your line of action, this distance here is the perpendicular distance for it, which corresponds to D2 from the diagram. So now you just need to think about the direction that it's going to push. So about point O here, this one, if you think about pulling on it with this Fx and think about it being able to rotate about point O, hopefully you can see that it's going to want to pull it in a clockwise direction, which would represent a negative in the equation. So this is equal to MRO. So whichever way you do it, you should get exactly the same answer for MRO, assuming that your system was identical. So FD in this instance is equal to Fy times D1 minus Fx times D2. So Again, just want to emphasize the method that you use here is really going to be dependent on the dimensions that you're given. If you're given the perpendicular distances for each of your forces, then go ahead and use them. But if you're given horizontal and vertical distances, which is probably going to be like 90% of the questions, then it's going to be in your interest to split the forces into horizontal and vertical components so that you're then able to just directly use these distances. So we'll do a few examples in the following videos, and yeah, hopefully that will clarify up any issues. So see you in those next ones.